Okay, let's talk about continuous functions now. So here we have this is a scalar valued function of a single variable, just a regular or normal situation of a function, y equals f of x. And here's another example of a function y equals f of x, single input, single output. This is different, right? Here we have some kind of picture. It's not even clear what this picture means, but it's definitely not a single valued, single variable input function. There's the input is x comma y, and the output is z. So that's not the standard situation, but these are just the standard situation of y equals f of x. So which of these, this one or this one, would we say are continuous? So probably you wouldn't say that this is continuous. But let's be a little bit more precise and talk about continuous at a particular point. So we probably wouldn't say that this is continuous at this particular point, whereas we'd probably say that this function is continuous at this point and at every point. Now, we would probably say that this function is continuous, say, here at B maybe, but not at A. There's some kind of jump here. So that's this basic definition of continuity when we're talking about scalar valued functions. That means the output is a single variable and the input is a single variable. So that's the standard understanding of what we mean by continuous. So she says here a function is continuous. If it's from R to R, it's continuous. If its graph can be drawn without taking the pen off the paper. So we can't draw this graph without taking the pen off the paper, so we say it's not continuous. Whereas this one we could draw without taking the pen off the paper. Now what about this one? So this says the graph of f, where f of xy equals 0, if both x is greater than or equal to 0 and y is greater than or equal to 0. So when both x and y are greater than or equal to 0, we're talking about this quadrant here of the xy plane. And so for values of x and y in this region, the height of the function is 0. So I guess that's why they've shaded this in. The height is 0. Okay, now what about here? Elsewhere, so anywhere else in the xy plane, if you choose any of those for your input, then the height will be 1. So I guess it's supposed to mean the height is 1 everywhere else. So, for example, we see this point here at 0, 0. But of course, 0, 0 has both the x-coordinate and the y-coordinate are 0. So the actual height at 0, 0 is 0, 0, 0. But I guess they're just identifying this point. It's not actually that height at 0, 0. When x and y are 0 and 0, the height is actually 0, right? Because this says greater than or equal to 0 and greater than or equal to 0. So, okay. Anyway, the question is, would we want, so this is what we mean by continuity for a function of a single variable. But how about in this scenario, that is for a function of two variables? What do we mean by continuity? Well, it's not clear yet, but would we want to call this function continuous? Probably not. Probably we would not want to call it continuous. But we could still be a little bit more clear, and we could say, well, what about at this point? Would we say it's continuous? Yes, at that point it's continuous, because in this area you can draw without taking it's not really clear what we mean by drawing because it's not as just a line. But anyway, this point we would say it's probably continuous, just like at this point B, we would say that this function is continuous. But like here, at this point, or this point, there's a jump. So we would say it's not continuous at those points, just like this function is not continuous at A. So she says we can try to extend this idea, that is, of taking the pen off the paper, to scalar value functions of two variables, like this picture here. A function is continuous if its graph has no breaks in it. Well, this graph has breaks in it, so we wouldn't call it continuous. But she says this way of thinking about it, or defining continuity, has some flaws. For one thing, we can't visualize graphs of functions of more than two variables. So this is a function of two variables, but if we had a function of 3 or 4 or 5 variables or whatever, we couldn't visualize that. And also, it's not always easy to make, it's not always easy to make a graph of a function of two variables, and to see what's going on. So that's another problem. So this idea of it has no breaks in it is a little bit hard to use. So we can, however, use the idea of limit to talk about whether a function is continuous or not. So let's call this function g and call this function h. And let's fill in some more for these graphs. So let's talk about a point. Let's say what is g of a? So I said that g of a is b. So I give that height, I'll call it b. And what is h of a here? So h of a, so you know that the solid dot means that the height at a is c, whereas the open dot means that the height at a is not b. Okay, so h of a is equal to c, not equal to b. Okay, now let's think about the limit as x approaches a of g of x. So as we get closer and closer to a here and get closer and closer to a here, what would we guess would be the height of g at a? Well, the pattern is that as we get closer and closer to a from the right-hand side, we're getting closer and closer, the height is getting closer and closer to b. And also from the left-hand side, as we get closer and closer to a, the height is also getting closer and closer to b. So we would think, and we would say, that the limit as x approaches a is b, but by b is g of a. So the limit as x approaches a is g of a. Now how about for this picture? What about for h? So what is the limit as x approaches a? So if we get closer and closer to a, well, if we're coming in from the right-hand side, then it looks like it's approaching c. But if we're coming in from the left-hand side, then it looks like it's approaching b. So here the limit doesn't even exist, much less it's not equal to h of a. H of a happens to be c, but in any case, the limit doesn't even exist here. So this gives us a clue as to how to define continuity in terms of limits. So if the limit exists, or if the limit doesn't exist, then we're going to say it's not continuous. But even if the limit exists, if it's not equal to the value of the function at a, then we wouldn't say it's continuous. In other words, suppose I had a slightly modified version of g. So suppose I had this for g. So by this circle, I mean that it's actually not, the height is not here. I can't really erase that blue line, but the height is not here, but the height is actually here. So still, in this case, for this particular picture, for this g, the limit still exists, but the limit is b, but that's not the same as the height, which I might call k or something. So the limit is b, but that's not equal to g of a. g of a is equal to k. So even when the limit exists doesn't mean that the function is continuous. The limit has to exist. Here it didn't even exist, so that's not going to be continuous. But even here, with this new picture, the limit exists, but it's not equal to the actual value at the point. So in that case also we wouldn't call it continuous. We would not want to call this continuous at a because it jumps up here. So that gives us the idea for the limit in terms of, that gives us the idea for continuity in terms of limits. So the idea is that the limit has to exist and it has to be equal to the function, a value of the function at the point A. So with this definition, we can easily extend our concept of continuity to functions from Rn to Rm. So she says, so how will we be able to tell in general if a function is continuous? So here's the definition. If f goes from Rn to Rm, let a be an x, then f is said to be continuous at a if either it's an isolated point of x. Well, we talked about that before. Let's ignore that for a moment. Or if the limit as x goes to a of f of x is equal to f of a. So now we have a definition of continuous that works for these kinds of functions. Now remember we did talk about isolated points. So if the domain of the function is x plus some point out here, which we called an isolated point. So according to this definition, if it's an isolated point, it's going to be called continuous there. Now this is not, remember, this is just a picture of the domain of the function. So if we have an isolated point in the domain, then we're going to call it continuous at that point. I guess because there's no way for it to not be continuous. Because for it to not be continuous, we'd have to be talking about the limit as we get closer and closer to this point. But we can't get closer and closer to this point because it's isolated. There's no path of points in x by which we could get close to this. So I guess they're just saying kind of by default, we're just going to call it continuous because we can't say it's not continuous there. But that's just a kind of anomaly. We don't really have to think about that, generally speaking. Okay, so let's look at this function. So we can test out this definition. So this is a piecewise defined function. So at 0, 0, we have one definition, and everywhere else, we use this formula. So at 0, 0, we're going to define the height of the function to be 0, and everywhere else we're going to use this formula to determine what height the function is. And we're going to ask, is this function continuous at 0, 0? So we have to think about this. We have to think a is going to be 0, 0. And we want to know, is it continuous at a or at 0, 0? So we said that the limit has to exist, and so this part has to exist, and then what we get here has to equal f of a. So we're talking about a is 0, 0, the origin. So, and we just said that f of 0, 0 is 0. So then we need that the limit exists and it equals 0 as we approach 0, 0. So what about? She says that the limit as x, y approaches 0, 0, as we get closer and closer to 0, 0, of this function doesn't exist. So if that's true, then we can already say that it's not continuous. So she says check what happens along the along y equals 0, which means along the x-axis, and then when along x equals 0, which means along the y-axis. And apparently we won't get the same thing, and so the limit doesn't exist. So immediately we can just say this is not continuous at 0, 0, because the limit doesn't even exist at 0, 0. That's like here, the limit didn't even exist at a, so we immediately can say that it's not continuous. Here, remember, the limit did exist at a, but still, if the limit at a is not equal to the value of the function at a, then we also have a problem. But first we have to have the limit existing. And here, first the limit doesn't even exist. So we can say it's not continuous. And she points out that this is the standard definition of continuity, the way we do it in first semester calculus, but we're not using vectors then, so this is not bold, and 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 this is not bold. So this is like a vectorized form of the normal definition of continuity. So she says that continuity looks the same no matter what the context, whether we're talking about single variable functions or vectorized functions. So how about polynomial functions? So we talked about the general form of a polynomial in an earlier video, and this was the general formula for a polynomial. So we want to ask, is it continuous? Are all polynomials continuous? But we proved earlier that, I think we sort of showed anyway earlier, that the limit as x approaches a of the polynomial is just equal to, you can just put in the components of a for the components of x. So that's exactly what we need for continuity, because what we're saying is the limit of the polynomial as x approaches a is just equal to p of a. This is just p of a. If this is p of x, and I mean x is vector x, this is just p of a. So the limit of p is p of a. The limit as x approaches a of p of x is p of a. That's exactly what we need for it to say that it's continuous. So now we've shown that any polynomial in n variables is continuous. Now what about this one? Remember, we just finished talking about this function. We just finished talking about this function in the previous video, and we just finished showing that if f is ax, that the limit as x approaches b of f of x, or of ax, is ab, which is f of b. So that means that all such so-called linear mappings, so this ab is called a linear, ax is called a linear mapping. So all these linear mappings are also continuous. Okay, so you can read this. She says, notice that the difference between this picture and the picture that we had before is that before we didn't write f of a, we had L there. So we said if we draw a sphere around L, so this is L. L is actually a vector, because we're working with vectors in this scenario. So anyway, we draw a sphere around L, and then we say, can we find a disk around A such that everything within this disk goes within this sphere, gets mapped to something inside the sphere. But if we want to show that something is continuous, then we don't want it to just be some arbitrary L. We want it to be precisely f of a. So the function is f. So we wanted, and we're asking whether it's continuous at a. And if it's continuous at a, the limit shouldn't be just some arbitrary L, but we want it to be precisely f of a. So that's why we have f of a here. Anyway, you can read this and make sure that you follow that. Okay, now we had some properties for limits, and we have some sort of similar properties for continuity, and that's because our definition of continuity comes from, or is, we use the idea of limit in our definition of continuity, so it seems reasonable that we should see some properties of continuity that are similar in form to properties of limits. Anyway, if f and g are two functions and they're both continuous at a, then the sum of f and g is also continuous at a. So remember, we can add functions, so we have two functions that are, let's say, so we have two functions that are both from R2 to R2, so the inputs are from R2 and the outputs are R2. Input is R2, output is R2. So what do we mean by adding these two functions? We just mean that you add them component by component. You add the outputs component by component. So you get, when I add the first components, I get x squared plus 2x. And when I add the second component, I get x plus y. So that's what we mean. So that's a new function. F plus g is the first component of f plus g is not x squared, it's not 2x, it's the sum of those. X squared plus 2x, sorry about this writing. And then the second component is x plus 2y actually. So that's a new function. So f plus g is a new function. But if f is continuous and g is continuous, then this theorem or this property here says that always f plus g will be continuous. Okay, the next one is if f is continuous and then we just make a scalar multiple of f, that will also be a continuous function. And here we have two scalar valued functions, f and g. Then their product, f times g, and their quotient, f divided by g not equal to 0, are going to be continuous. And then this one, okay, this one is a function f is continuous at a if and only if each of its component functions are continuous. So if we have, if we know the component functions and we show that they're all continuous, that means that the f is continuous. So for example, here's a function from R2 to R3. So it has input is R2, but our output, there are three elements or three component functions. Now it's a little bit, we haven't been talking much about sign, but nonetheless we have three component functions. Then if we can show that each of the component functions is continuous, then we will have shown that f itself is continuous. So she goes through that, and you can check this. Okay, one more. So we talked about up here the sum of two functions. If both f and g are continuous and the sum is continuous, if f is continuous and you multiply it by a scalar, then that's also continuous. The product of scalar functions are continuous. So we talked about that, but there's one operation we left out, very important operation for our purposes, is composite functions. So that means f of g. So this operation, f of g, which is called f circle g, that's the name of it, but it means this, f of g. So if f is continuous and if g is continuous, what about f circle g? This is f circle g, or f of g. Is that also continuous? So what does it say? If f is continuous and g is continuous, notice that this is Rn and this is Rm, but this is not the same, right? These are different. If you think about doing function composition, you see why you have to. It doesn't have to be the same, but this has to be the same as this. So just think about it. Anyway, if f is continuous and g is continuous, then the composite function g circle f is continuous. Okay, and then we have the proofs come next. And then we have some problems which we'll do in the next video.